So I'm excited to introduce Carmit Hazay. She's an associate professor at Bar-Ilan University, and Carmit and I, as he said yesterday, we shared office at Aarhus when we were postdocs, and we shared a lot of exciting chats together. And I used her like an oracle for a range of questions, starting from how to manage a kid to how to improve UC security. So I'm really excited that she's here and second time in India. And today,
third time in India, second time here, third time in India.
Yeah. Oh, in TCC. Yeah. So today she is going to tell us about diagnosis, lightweight, scalable RSA modulus generation with a dishonest majority.
Thank you. So first of all, I want to thank Art TAHE for the kind introduction and also for inviting me here. It's a pleasure. And this is a very exciting project, as I hopefully will be able to show you and convince you. And it has been carried on with a fantastic set of people. On the academic research side, it has been, the collaborators are Megan Chen, Yuval Isha, who's sitting here, Daniela Michancho, Abhishelat and Mutu. And we also have a fantastic set of engineers that still been working on this project. Yuri Kashednikov, Tarek Riveri, and Ruan Bang. All right. Good. So let's start with the goal. We have a set of parties. That would like to interactively and jointly sample a biprime modulus R. This is what we call an RSA composite, a product of two large primes, such that the secret key or the secret components is secret shared amongst the parties, and no one actually knows the actual product. It is a secret. Only if all parties collaborate, then they can extract P and Q. And our mission is to design a protocol that can run with 1,024 parties. Not only that, we want the pretty much the strongest type of security in the dishonest majority setting with active security, meaning at most n-1 of the parties can collude, and even if only one party chooses the shares appropriately, as the protocol specifies, then the result is secure. No one can extract the prime products of the outcome. Why do we want to do that? So let me give you a toy example. So here is a function that is provably shown to be inherently sequential, meaning that if I give you a very large integer, say 2 to the t, of size 2 to the t, computing this function will require sequentially t steps. And you shouldn't be able to use, let's say, dedicated hardware to improve the computation or paralyze the computation, in a sense. You will really have to go step by step. And this is a known function due to Rivest, Shamir, and Wagner, which show that if, let's say, some designated verifier knows the prime product, it could verify this, the outcome of this computation faster than actually computing it. And these type of functions have been turned very useful. Also, specifically for the blockchain applications, where for blockchain, we would like the verification process to be public. So we don't want anyone to be using the prime factors to verify the outcome. And there have been follow-ups recently by Pierczak and Wasilewski showing that how to actually verify this function publicly. And so this function is called VDF, verifiable delay function, where computing them takes a certain amount of time and verifying the outcome is presumably faster. And they have attracted a lot of attention recently due to many potential applications over the blockchain. Specifically, Ethereum Foundation, which is a platform, non-profitable platform that coordinates research and development over the blockchain, has this huge project where they wish to run a ceremony for generating this RSA product, RSA composite, and then hard code this RSA into dedicated hardware like ASIC. So they're investing a lot of money into that. And how our team comes into the picture? Precisely. So we design the protocol that they're going to execute during this ceremony. And how do we do that? This is exactly the goal of this workshop. We're going to use secure computation. This is a classic application for secure computation. And in some sense, what I'm going to say, I gave you a particular application, but you can generalize it to many more applications, meaning the tools I'm going to explain can be used for many other applications. It's very useful. And you could also view my talk as a complementary talk to Peter's talk from yesterday. Because if you remember, Peter explained about the online phase of certain protocols, neglecting the offline phase. And basically, the process going on in the offline phase is generating some correlated randomness, right? Let's say authenticate triples is one example. So you can think of this protocol as a protocol for generating triples. Good. So very, very quickly, so in secure computation, what's the setup? We have a set of parties with secret inputs, and their goal is to compute some function. As opposed to Manoj's talk, here they actually know why they want to compute the function. And some important properties required from these outcomes, which you've heard a lot in the past few days, like privacy and correctness. Okay, so let me give you a little bit overview of the processing of works that developed protocols for this functionality, for the RSA functionality. So the paper that actually started this line of works, so it says 01, the year, this is the journal version, it was published in 1997 by Bonen Franklin. That was a seminal work in this area. So they designed a protocol in the honest majority setting, exactly the classic BGW protocol you've seen in the first day, with semi-honest security. And I'll say more about their protocol. I just want to show you some. This is like a partial list of follow-up works that basically sort of use the same blueprint introduced in Bonen Franklin, but gradually improved it. So let me say a little bit about the Bonen-Franklin framework. So the protocol has 3 main steps. In the first step, the parties jointly choose their shares for P and Q. And we're talking about additive shares. Throughout the entire talk, I'm only talking about additive shares. They also have another phase combined with this candidate sharing process, which is called trial division. So the main bottleneck in these protocols is kind of an objective bottleneck, meaning if we choose the shares of the prime together, we have less control whether we hit the prime or not. And now the question is, how often do we hit the prime? Because this probability will determine the number of iterations we will need to run over and over and over again, or basically how many trials our protocol will require. So you would want, if you design a protocol for this purpose, to minimize the number of trials. Good. So the trial division basically says that if we can, before we compute the product, if we can check each prime separately and check whether it is divisible by a certain bound of the first, let's say, 100 primes. Okay, this is some bound. The bound is actually a parameter to the protocol because there is a trade-off. So if I can first run a trial division and then eliminate all the prime candidates that do not pass the test, then I can substantially reduce the number of trials. So this is what they do in this first phase. In the second phase, they compute the product, and then they have they designed a biprimality test that takes the RSA composite or the candidate and checks whether it is actually a product of 2 primes. So these are the 3 main steps in their protocol. And following their very influential work, there has been quite many papers improving on their work. And there are several aspects you can think of improving their paper. For instance, they had passive security in the honest majority setting. So a paper by Damgaard and Mikkelsen showed how to design a protocol. So they started with a 3-party instance, which can basically extend it to like any number of parties, but the overhead is quite large because they use a specific type of secret sharing. It's called replicated secret sharing. And another thing they actually achieved together with active security, they used a different primality test. So in Bonen-Franklin, they didn't use a primality test. They had a trial division. And then they had a biprimality test. One could think, let's generate the shares of the primes and then test their primality. But remember, we're not allowed to reveal those primes. So the test must be executed in some oblivious way. So this is what they do here. So they first compute, we go to the next slide. They compute a version of the Rabin-Miller test, modulo the composite, which is given, already revealed by the protocol. And then they use MPC or 3PC to reduce it, but modulo an unknown secret modulus. So this is this part was the expensive part in their protocol, apart from the fact that it was only applicable for 3 parties. Okay, in a follow-up work, the project which I was involved in, we use a slightly different mechanism to run the trial division test I was mentioning before from Bonen and Franklin. So we started with a two-party protocol, but could extend it to the multi-party setting. And we had slightly small, can you read it? It doesn't really, more than I can say, that we used additively homomorphic encryption to basically encrypt the shares of the prime, reconstruct the prime encrypted, and then check whether the encrypted prime is divisible by all the small primes from some bound. So that was quite expensive because the computation or this test was performed over the ciphertext. And then to check whether it is divisible, you basically want to check whether it is divisible by all the product of some prime. And you actually need to decrypt the ciphertext, and you need to do it in some secure and private way. So that was the mechanism that we used in that paper. And then we used another layer of homomorphic encryption to compute the product. So far I gave a short overview of dedicated protocols for this functionality. Well, maybe except Bonen Franklin that used BGW. But you might think maybe if we use more advanced techniques of generic MPC, we might be able to come up with better protocols or more efficient. So this was tested and checked by Shalat and Chen, where they designed a circuit, a Boolean circuit for this task. This is the RSA 256, means that it computes the product of only 256 prime, bit prime, two primes of 256 length. And actually, I'm not even sure I was very concrete about the size of our composite. We want it to be 2048 bits, product of 2000 bit primes, which is much, much higher than what they actually checked here. And you can actually see that the size of communication, this is the second line, is 3 terabytes. It's huge for much simpler tasks than what we are looking at. So I'm just following you a process of our thought when we try to understand how to design a protocol for this task. Going towards or using generic protocols as is, as you can see, wasn't really useful. And a last paper I'm going to mention here is a very recent paper by Fredrickson et al. From Crypto 18, where they designed a very efficient protocol. They implemented the protocol in the two-party setting. And their improvement came from using OTs to compute the product, not just the product, other building blocks, which I'm going to show you next. And since OT is a very, you already seeing, is a very useful, is a very well-studied primitive in secure computation, we actually have very, very efficient implementations for OT extension, which I believe also Peter is going to talk about tomorrow in his talk, right? Tomorrow or Wednesday, at some point, he's going to talk about it. So they used OT here, and I'm going to show you how it is done. But before I'm going to say more technical stuff, so summarizing the discussion and maybe state-of-the-art works at this point, If you want to use techniques existed in the literature so far, so generic protocols had the implementations reach up to the order of 100 parties. For specific and dedicated tasks, we had a recent paper by Dorner et al. That showed how to do distributed signature scheme, where there the implementation but a little bit higher than that. And so how do we proceed from here? Our protocol, or the protocol we want to design, has much higher scale. We are talking about 1,000 parties. So let's try to understand how to address such a task. What would be the protocol blueprint? So the first question we asked ourselves as the team, what would be the best passive protocol for this task? Let's start with it. And then we will understand how to compile it into the active setting. Okay, so great. So what's the best scalable passive protocol? So again, what's the starting point? We want to design a multiplier, or a protocol that computes the product. Let's start with what we know exists in the two-party setting. So what's a multiplier protocol? It takes two strings and it computes the additive shares of the product. And this is a very fundamental functionality that is basically, you can abstract pretty much any generic 2PC, MPC with this functionality. So what's the building block? And this is why OT is very, very useful. OT is used to realize these functionalities. So very, very quickly, let's recap the functionality of OT. We have a sender and a receiver. The sender has two strings or 2 bits, and the receiver has an input bit. And the goal is for the receiver to learn S sub B without learning anything about the other string, while the sender doesn't learn anything about the input bit of the receiver. And it has been mentioned before, OT is the complete functionality for secure computation. You can compute OT securely. You can basically compute any efficient functionality securely. We have very efficient implementations, both passive and the active setting. And it implies very, very fast secure Boolean implementations, mostly in the two-party setting. Good. So how do we implement a multiplier from OT? And this is a classic by now protocol by Gilboa, who is also going to talk at this workshop. And this protocol works as follows. You take the receiver's input string. Remember, the party's inputs are strings of, let's say, L bits. And you decompose it. You bit decompose it into bits. And then for every bit, such bit, you have you carry out and run an OT execution. And then you combine. There is a very simple way to combine the outcome of these OTs, and you get the additive shares of these two of the product. And the downside of using this protocol is that the communication complexity grows with the size of the original receiver's input times the communication complexity of the OT, which is order of kappa. Maybe it could be even done faster using I don't know new techniques, but basically it grows. It depends on the length of the receiver's input. Now. An alternative approach would be to use a generalization of OT, an object called OLE, Oblivious Linear Evaluation. And here, the party's inputs are given over some field F. And the goal is for the receiver to learn some linear function of the sender's input so the a times x plus b. And it's a very simple exercise to see that OLE is an extension or generalization of OT, only that it works for a larger fields. So it seems like it's more appropriate for our needs because the parties' inputs comes from some larger domain. Okay, so a very simple protocol to compute OLE is based on additively homomorphic encryption. So it already mentioned before, very briefly, it's an encryption scheme where a receiver giving two ciphertexts can compute, can run some operations on the ciphertext which are translated into addition, or you can extend it to any linear function over the plain text. So from the ciphertext given a and b, you can actually compute the ciphertext a plus b without knowing anything about a and b. And here's a very simple protocol that implements the OLE functionality. You start, the receiver basically sends the encryption of its input. The sender, using the homomorphic properties of the underlying encryption scheme, computes the evaluates the ciphertext, computing the encryption of a x plus b, and it all turns. I mean, the receiver just needs to decrypt the outcome. Great. The downside of using this protocol is that OLE typically, at this point, is typically less efficient or slower than the OT, and the implementations we have today are do not reach the do not achieve the overhead we have with OTs, and I just want to mention that we do have, or let's say the most efficient implementation we have today is based on lattice-based crypto. You could do batch evaluation. Yes? I couldn't hear. Not as far as I know, but I think Yuval will know the answer even better. Okay. So we do. I guess. Okay. So yes, I guess there is, and Peter will be discussing. It's an extension of the silence OT line of work. So far, I only described protocols in a two-party setting. So what about MPC? So one approach would be to extend in a more naive way the protocols I was discussing before, and have defined an OT or an OLE channel between every pair of parties. And this, in part, is the main bottleneck we have in MPC protocols today, or in the implementations we have today, because the bottleneck is the communication grows quadratically with the number of parties, and this grows up very quickly. So if you want to design a scalable protocol, we need to take or to consider an alternative approach. Good. So here is the building blocks that we are going to use for this purpose. So let me introduce threshold additively homomorphic encryption. Here, it's a primitive where none of the parties, or any even strictly subset of the parties, cannot extract the secret key. So basically, the secret key is shared among the parties. So we will have a protocol for distributing for having a key generation. Encryption is as before, and for decryption, then we will have again a protocol where each party basically partially decrypts the ciphertext using its own share, and then you aggregate all the partial decryptions into the actual decryption. And threshold additively homomorphic encryption has been very useful in reducing the communication from quadratic to linear. And these ideas are not new. They have been, yes? Question? Okay. These ideas are not new. They appeared in the literature before. Concretely, we have the Franklin-Haber protocol. They designed a semi-honest protocol based on threshold additively homomorphic encryption. And then a follow-up paper by Kramer, Damgaard, and Nielsen, which used this primitive and dedicated zero-knowledge proofs based on number theoretic assumption to achieve actively secure protocol. Their protocol was shown in the honest majority setting, but you can easily extend it. The same ideas follow for this honest majority setting as well. So these ideas are not new, but they were not been, let's say, examined or implemented for practical purposes until this point. Okay, so this is what I've mentioned before. And now let's see a protocol which is used to compute the product, a very simple protocol. And you could actually use it to generate other types of correlated randomness, as I mentioned before. Right? So the starting point, we have n parties. They choose shares for P and Q. And first, they run a protocol for generating the public key and the secret key shares. Next, each party encrypts its own share of P. And you can think of, let's say we choose one of the parties, you can think of him as an aggregator. Like he's the party that gets all the ciphertext. And you could combine them together into the encryption of P and then send back. So now everyone have the encryption of the first potentially prime number. Now, in the second, like in the next phase, the parties homomorphically compute the product of their share of the second prime candidate with this with P, and again distribute or send these values to this coordinator, which aggregates the ciphertext and distribute back the product of P and Q, and the parties just run a decryption protocol. So it's a very simple protocol that is used as a multiplier. All right. So, so the next question, now that we understand what primitive we want to use, we need to instantiate it, right? So what is the actual building block or encryption scheme we can use for instantiating this, this protocol? So let's try and understand what kind of candidates do we have in practice. So we have Multiplier. Why can't we use Multiplier for here? Because it's basically a cyclic choice. Because the public key of Multiplier is an RSA composite. And this is what we want to generate from the first place. So it doesn't help us. What about El Gamal? What's the problem with El Gamal? Well, if you want additively homomorphism, it operates in the exponent, right? So you need, it's inefficient to decrypt. You can use El Gamal with additive operation only if the domain of the plaintext is very small. So you basically do brute force when you decrypt. LWE, fantastic, is a great object. The main issue with LWE was that it didn't support fully what we call SIMD operations. Let me try to explain. We want to be able to conduct many operations in one shot, in parallel. So SIMD means single instruction, multiple data. So I would like to encrypt a vector or a block of elements and then perform either an addition or a multiplication with the scalar at one shot on many values. And LWE does support packed addition, but not multiplying with a scalar. So originally we actually thought we were going to use LWE, but then it didn't reach the performance we needed. So what's left? Ring LWE, and this is essentially has the properties we needed from the encryption scheme. It even supports better parameters. But part of the contribution in this project is identifying the precise values, the precise parameters that could be instantiated with ring LWE for the purpose of having threshold additively homomorphic encryption. And the reason it supports packed operations is because you can view the ciphertext and the plaintext as a polynomial. And now you can encode within a single ciphertext a block of values that are basically encoded within a polynomial. And then operations on polynomials work as we expect them to work. Like you could do, you can add two polynomials as you've seen in the first day, and you can also multiply with the scalar for a bunch of values. So it worked perfectly. So now let's continue for another type of optimization we would like to incorporate. So I was saying before that we want to generate primes of length 2 to 24 bits sizes. So the first phase of the protocol naturally is generating the candidates and running some trial division. This is essential if you want to reduce the number of tries. The probability of hitting a prime number without running any test is 1 over 2 to the 10. This is a well-known theorem. So that means that if we just do naively our prime sampling, say on the average, the number of trials per one prime is order of 1024, even more. And you need to do it twice. So it's multiplicative probability, which is very bad. So I mentioned before, you could do a trial division that improves this analysis by checking whether this candidate is divisible by 3, 5, 7, and just go on until some bound. And you'll see there is a trade-off because this test also costs something. So in previous two papers, as I mentioned, in the paper I was involved with, we used El-Gamal encryption scheme, and we did this test in the exponent. Right here, we could use El-Gamal because you don't really want to decrypt. You only want to check whether, basically a predicate, whether some encrypted value is divisible by a prime or not. It was improved by the FLOP paper, Fredrickson et al. Let me show you how they did it. It's a cute trick. Basically, they used OTs to check for divisibility. So let's say we want to check whether the shares of some prime, potentially prime, are divisible by the additive shares together are divisible by 7. So you use a 1 out of 7 OT. And basically, what you do is you reduce to random OT, where each value is translated to some other random value in this domain. So if you run the OT, what's left to check? Whether the addition of these two random values are equal. Because, I mean, modulo 7. That's basically what you want to do. And now, that's what they did with basically every small prime. Like for 3, for 5, for 7, and so on. Whenever you hit some, whenever the test fails, then you just eliminate this candidate. So on one hand, OT is very relatively cheap. We have OT extension, and you can reduce, but definitely in the semi-honest setting, to all these instances to one of the two OTs, relatively easy, but still it has its overhead. And the higher the bound you fix, the many more OTs you need to engage in. And this was a protocol that was carried out only in the two-party setting. Extending it, as I was saying before, will be too much expensive for us. So here's another optimization. All these protocols first computed the prime and then tested. What if we could reverse this to sort of the order of this protocol? What if we could first test and then compute? And it's basically pre-approve the shares we want to use. So how do you do that? You use CRT. Again, I mean, CRT has been used in many, it was out there. It wasn't used in this context. So you can assume that the domain from which you want to sample the shares is a domain where it could, is a product of smaller values. And then you use CRT to sample directly from the smaller domains. And whenever you, testing each such domain is much easier than testing the big one. So you basically sample many shares from the smaller domains and then test, or basically you make sure that the shares you sampled, they're not divisible by some small set of primes. Now, all this process is much, much more efficient than testing it for 1,000 bit prime, let's say. Because this could be as small as 30 bits, but very small. And then another observation is that the reconstruction algorithm is a linear function. And we are anyway working with additive shares of the primes, right? So the parties can reconstruct their big share out of the small shares locally. No need of communication at all. So this made a difference in terms of the analysis, reducing the probability of hitting a prime, because now the analysis condition on what we already know, that our candidate is not divisible by some set of small primes. And the probability of hitting a prime under this condition reduces to 1/60. Much, much smaller than what we had before. So since you need to hit a prime twice, so it boils down to 1/3600. And this is like, let's say, much, much less candidate than what we had needed to suffer based on the previous analysis. And this is just the biprimality of Bonen-Franklin. It's here as is because here we didn't optimize anything. We just used it as is. I just want to say that the error probability in their test is half. This is a worst case analysis. But when you run this protocol in practice, the error probability behaved much better. So usually for most of our candidates, we did not need to test more than twice in order to eliminate a candidate. So it behaved fantastic in practice, and usually many times the empiric results could identify something that we should explore in theory also. And that means that we could probably improve, greatly improve the Bonen-Franklin analysis. Good. So let me give you the framework. Remember, we're still in the passive setting. So this is our framework. We start with what we call, this is now the pre-sieving. Remember, before we had the sieving, you do the elimination after you compute you generate the primes. Now you do the pre-sieving, and then you have the CRT reconstruction for generating the shares. Then you compute the multiplication. You run the multiplication protocol based on the threshold additively homomorphic encryption I specified before. And then you do the biprimality test. Great. So that's the framework for passive security. And actually gave very fast passive protocol. Our implementation showed that for 1,000 parties, you could actually run it in less than 5 minutes. 1,000 parties. Remember, before, we couldn't reach more than the order of 2,050 parties. So that was very exciting. And then one night, we were trying to define what kind of experiments we're going to run. And then Abby came with this question: why do we stop at 1,000? Why can't we do 10,000? So this is like, wow. We didn't even think to try to reach beyond 1,000 because we were so dedicated for this task. Let's do it. It took the engineers 3 full days and nights to configure the Amazon instance. Remember, they needed to configure this huge network on Amazon. And then we had 2 tests. I can show you the numbers at the end. On the average, they took half an hour. And that was so exciting. We didn't even believe we can actually run such a large instance on MPC. And I hope you share my excitement, because this is really going beyond the limitation we had so far for MPC, even for passive security. Great. So let's talk a little bit about achieving malicious security. So how do we compile a protocol? What do we do? Let's go back to the classics. What does it mean? The GMW paradigm. So this protocol wasn't explicitly explained in this workshop. So just in one sentence, it uses zero-knowledge proofs to make sure that every party basically attaches to its next message, next outgoing message, a zero-knowledge proof, proving that the message was computed correctly with respect to all previous transcript and some committed input and randomness. And also, this is like classic, one of the first protocols we had, one of the first compilers we had in MPC, both for, we had passive and active security. But it hasn't been really used for practical purposes so far, because it has been believed that generating the zero-knowledge proofs would be very expensive. So that was another thing we tested in this project. Now let me be more specific about the network topology of our protocol. So I was hinting before, but now I'm specific. We have the end parties, and they communicate with this coordinator. This coordinator does not introduce any input to the computation, so it doesn't have any secrets. We just rely on its computational power. So this coordinator will do the aggregations I was mentioned it before. Remember in the threshold protocol where parties send the ciphertext, someone is combining all the ciphertext, sends back. And since all the operations this coordinator is doing are based on public information on the transcript, anyone can verify. So you can define a bulletin board where you can put the coordinator can copy there all the transcript as well as the messages it sends back. And anyone who has access to this board can verify the computation of this coordinator. In the protocol, okay, the parties themselves will use zero knowledge proof to prove the correctness of their messages. And let me just first tell you what were our performance targets when we started this project, because it wasn't arbitrary. So, as I mentioned, we had 1,024 parties. We were restricted to 200 megabytes per party. That's it. That's very small. If you think about the communication that you need to produce, not just for generating the product, also for the zero knowledge proofs. And we were restricted with the number of rounds, at most 12. And the protocol, when the ceremony itself, when it will be executed, must support like even very, very slow participants. We are assuming like the minimal configuration for this participant. We are allowed to use a very, very powerful machine for the coordinator. Take the strongest machine you can sort of configure on Amazon. That's okay. Now the question, again, what zero knowledge shall we use? So it's natural to think we have great zero knowledge proof systems that we can actually embed in our MPC systems. But we have so many. They introduce different trade-offs, right? I think Chaya was talking about it yesterday. So for the purpose of this project, we identified what are the properties we require from our zero knowledge proof. We want it to be transparent. So you can also collapse the round. It must be memory efficient, definitely at this scale. And it should maybe support or be friendly, commit and proof friendly. So this feature is important because, as I mentioned before, in this paradigm, GMW paradigm, the parties first commit to their, no input here, right? First commit to their randomness, and then prove all their actions with respect to the randomness they're committed to. So it must be very friendly designed with respect to this feature. And there are several zero knowledge proofs that are transparent and you could actually use. But the most memory efficient one, even up until today, is a joint work with Yuval and Mutu and Scott Ames. This is a Ligero proof system, which is based on the MPC and the HES paradigm and achieves sublinear proof length, order of square root, circuit size. And even up until today, it seems to be like it's a 3 years work, 3 years old work paper, and ever since there's been a long list of improvements. But up until today, in the ballpark of transparent sublinear zero knowledge based on symmetric key encryption, symmetric crypto, it seems to be the most memory efficient and computationally efficient on the prover side. And that was very, very extremely important for our project. due to the large scale. Okay, so very quickly, let me just say that recap the protocol I had before for the threshold encryption. So here you could say that you need a zero knowledge proof for proving that, remember we're using ring LWE, so you want to prove that the shares of both the encryption scheme and the primes came from the right domain. Especially, it's important for lattice-based encryption schemes because you somehow want to bound the noise. So these encryptions work by adding some noise and it aggregates. So you don't want to cross some bound because otherwise correctness is not ensured. So we used range proofs, and we used we actually composed. I think Chaya mentioned it yesterday. This paradigm of composing statements based on different paradigms, like Sigma protocol and generic-based zero knowledge, and we do something similar. I will not get into the details, but that was also challenging and interesting to design. And these are the steps of our protocol. We generate the threshold parameters, the encryption scheme. We sample, we do perceiving, we sample the prime measures, use homomorphic encryption to compute the product. We run the probability test, and then at the end we run the certificate part when we this is another point, because in GMW you have to run a zero knowledge proof per step. Here you can push it to the end, also because these functionalities do not have, this functionality doesn't have any secret input, right? Only secret randomness. So this is like an intuitive argument, but it wasn't very easy to prove that intuitively privacy is not violated because if an adversary cheats throughout the protocol, eventually it will get caught, but it couldn't violate anything throughout the protocol because no secret input. So intuitively it seems like very natural, but it was quite challenging to also prove security and write a simulation for this this proof. And this is concluding. I don't know if you can see. So basically, these are the graphs we had for the passive implementation. The bottom line is that we were managing to run like an instant of 10,000 parties, which was really great. That was 2 months ago, and very, very soon, say hopefully in 2 days, we're about to finish the implementation, also the active part. So I don't have any concrete numbers to tell you, but the recent update I received from Mutu this morning is that they had an experiment with 100 parties, and the bottleneck was on the verification side. The coordinator gets, like, think of thousands of proofs, and it needs to verify their correctness before it moves on, and that took almost 10 minutes. But they know not to worry. They know how to parallelize the process and reduce greatly this time. So it should be much faster. So hopefully next time I'm explaining about this protocol, I can actually give you concrete numbers for the entire implementation. So this is a good time to thank everyone who was involved with this project, and to you for listening.
Questions?
What?
Mutu is doing the hacking?
Mutu is the one that what?
Hacking.
Hacking? What, the protocol? Yes.
Yeah, so you mentioned the threshold AHE protocols, and like they seem similar in spirit to what the speeds family does in the offline phase. So you also mentioned that there was no concrete implementation of it.
Not exactly.
Up till now.
They do. So there are two types of implementations so far. One based on OT, which is Peter's work, mascot, and one based on somewhat homomorphic encryption scheme, where you the encryption scheme supports one multiplication, and neither of the implementation actually use threshold instance.
Like I think Overdrive does use this
Right. So no, actually, Overdrive doesn't use, I think, a threshold instance as well. I think we checked their. So the point is that first they use dedicated zero knowledge for lattice based because they proved that the parties computed the triples correctly, and they generate authenticated triples. So it's a different functionality. And as far as I remember, they did not use threshold, but I can check it. We can take it offline. I can check it.
Okay. Thank you very much.
Sure. Somewhat homomorphic, right? Not additively homomorphic. Yes.
Okay. Thank you very much.
Any other question?
Rotations for the additive homomorphic encryption?
Can you start again?
Do you have to do rotations
For what?
in the additive homomorphic encryption based on the ring LWE? To do the bats when you do like
the ring LWE?
yeah, do you have to do rotations there? Because
Yes,
rotations...
I think you do. You need to do it. Yeah.
Oh, and it took 5
I
minutes
think-
with rotations.
No, the 5 minutes were. This is for the passive.
Yeah, also for the passive, I guess you need the
Oh,
rotation.
yeah. Yes,
Oh, okay.
definitely.
What kind of network would the experiments run over?
What do you mean?
So for like 1,000 parties, were they all in a LAN or
No.
wide area?
Spread over 5 continents.
Okay.
And as spread as possible.
We tried to find one on Mars, but
But Amazon didn't reach there yet.
And using the proof, do you just check
Who
the
said? Yes.
do you just check the range of the noise or also the distribution of it? Using the
No,
data?
you check the range of the noise or something.
Okay, then why do you prefer? Does bulletproof not do better than Ligero in that aspect?
No, bulletproof. In bulletproof, the prover is much less efficient.
Right.
Needs to do exponentiation. It grows with the size of the computation.
Okay.
Ligero is symmetric based scheme, so it's no one, neither. Yeah, but and also the verifier definitely, but the prover is the real bottleneck, and no one, neither of the older or the same the schemes that came out at the same time beats the Ligero in that in this domain.
And to get commit and proof, do you just use SHA commitments and check the proof in every time? Or,
Sorry, I couldn't hear. I can use
for
what?
Commit and proof
Yes.
in Ligero. What is the commitment that you use?
It's part of what we use in the Ligero scheme. It's a Merkle tree based commitment scheme.
Yeah, so I think, are there more questions? No? Yeah, so yeah, let's thank the speaker.
Thank you.
And do I have the usual stuff for you?
Oh.